Humanity has remained within 400 miles of Earth for over half a century. Since the final Apollo mission in 1972, every human spaceflight has been confined to this narrow band. The Apollo missions were the product of a Cold War sprint to the lunar surface. Today, the objective has shifted from simply visiting the moon to establishing a permanent, sustainable presence there. This effort begins with Artemis 2. In 2026, the Space Launch System will attempt to carry a crewed vehicle back into deep space. The four-person crew includes the first woman, the first person of color, and the first Canadian assigned to a lunar flight. Launching from Florida provides just enough energy to reach orbit, but the Earth's gravitational pull keeps the spacecraft locked in a circular path. Breaking that circle requires a second, high-stakes operation. The success of the entire mission depends on a single maneuver occurring 25 hours after liftoff. This threshold is known as the Trans-Lunar Injection, or TLI. To escape Earth's orbit, the crew must trigger a massive, timed release of energy to propel the 50,000-pound Orion spacecraft toward the moon. If the engine fails to ignite or stops prematurely, the mission ends immediately, leaving the crew stranded in Earth's gravity. The TLI is the ultimate commitment point. Once the spacecraft achieves the required velocity, the crew is on a trajectory that leads hundreds of thousands of miles into deep space. The lead-up to the burn is unusual. Shortly after reaching orbit, the Orion capsule separates from the main rocket's upper stage. This allows pilot Victor Glover to take manual control, flying the capsule around the discarded rocket stage to test the spacecraft's handling and sensor arrays. However, by separating from the upper stage, the crew can no longer use the heavy rocket engines to reach the moon. Propulsion and life support now rely entirely on the European Service Module, or ESM, which is attached to the base of the capsule. The ESM's main engine is a refurbished unit that previously flew on 6 missions aboard the Space Shuttle Atlantis. The ignition of this repurposed hardware is what determines if the mission moves forward. At precisely T+25 hours, the crew initiates the TLI. The engine ignites for 5 minutes and 55 seconds. The engine must accelerate the vehicle by exactly 1,274 feet per second. This specific increase in velocity is what allows the spacecraft to break Earth's grip. This acceleration transforms the circular orbit into a stretched ellipse that reaches out toward the moon's position. This creates a free return trajectory. By using the gravity of the Earth and the moon, the spacecraft follows a figure-8 path that naturally carries it back home. This path functions as a gravity-based safety net. Even if the primary engines fail after the burn is finished, the crew will still return to Earth. A successful burn commits the crew to a 10-day journey, passing roughly 6,000 miles beyond the lunar far side. This trajectory will break the human distance record from Earth, currently held by the Apollo 13 crew. Reaching this distance allows NASA to stress test the life support systems and communication arrays in the harsh environment of deep space. The mission validates the ESM's reliability and confirms that the redesigned heat shields can withstand the 25,000-mile-per-hour re-entry speeds required for lunar return. Successfully executing the TLI and surviving the return trip proves the transportation system is ready to ferry crews to the moon. It validates the vehicle needed to deliver the personnel and hardware that will eventually build a permanent lunar base.